Hello and welcome everyone to another Applied Flow Technology webinar. My name is Nick Vastine. I'm a business applications engineer with Applied Flow Technology, and today I'm going to be walking through an introduction to resistance curves and some best practices to implement into your own models. So the agenda today, again, it's a relatively simple concept, so it won't be too intensive. First, we'll talk about what is a resistance curve. We'll talk about why a resistance curve is valuable in the sense of hydraulic modeling. What information do we need to define a resistance curve? With that, we'll touch on the concept of reference density and how that can impact your results. We'll discuss some of the common pitfalls that you want to try to avoid. Again, you attending this webinar and watching it is a good first step to avoid these common pitfalls. And then finally, how can we troubleshoot resistance curves if they are causing convergence issues within a model? So the first question is, what is a resistance curve? A resistance curve is a user-defined head loss at various flow rates. A way that we can think about it is we have a curve that we've fit to a particular component. This could be a valve, it could be a screen, a heat exchanger, where we know a specific head loss or the amount of pressure loss through a component at a given flow rate. We can then curve fit that information, so that way if we're not operating at that same exact flow rate, let's say we're making other changes to the system, replacing a pump, removing scaling on piping, we can see how that flow rate will change and also how the pressure loss through that specific component will change as well. So these resistance curves should follow a quadratic relationship. So again, we should see that increasing slope as we increase with volumetric flow rate. And that's going to be consistent with a lot of the other pressure losses that we see in a hydraulic system. So for example, the Darcy-Weisbach equation, which is for pipe friction losses, we can see that same velocity squared term as related to the pressure loss. So as you double your velocity, you actually quadruple your pressure loss. The CV and KV loss model, which is more common in valves, we can see that Q component, which would be here our volumetric flow rate, V again proportional to that volumetric flow rate. It's that component squared. That's equal to our pressure loss. So again, doubling our flow rate should quadruple our pressure loss. Finally, we see that same relationship with K factor losses, where we can also take a resistance curve that we've defined, and we can also define a K factor and define our components in that way. Another thing to consider is that if we look at these as quadratic equations, we only have that squared term. We don't have a linear changing proportionally with velocity or with flow rate, and we don't have an initial pressure loss term. Again, think about it conceptually and think about it from fundamental physics. We can't have a frictional pressure loss if we don't have any volumetric flow rate. So as we'll see in later slides, we should always have this 0, 0 point, where at 0 volumetric flow rate, we should see 0 head loss across a component. That can introduce some uncertainty in your analysis. For example, if you have a closed valve, you might see a head loss across it, but it's important to recognize that that closed valve is not creating that pressure loss through friction. So a few things to look for. Again, we want to see this quadratic shape. We want to see this 0, 0 curve, and we should not see a y-intercept on this quadratic relationship. So why are resistance curves valuable? Why might you use that instead of defining a valve in terms of CV or a loss factor in terms of K? It's because resistance curves are very versatile and they have a lot of flexibility to capture losses of very different components. So for example, within our software, within AFT Fathom, Aero, Impulse, and Extreme, we include loss models for these different components. So things like valves, orifices, which depend on area change depending on the angle, and the incoming and outgoing areas. And all of these losses are usually defined from empirical evidence that we can take and extrapolate out to say, given this change in piping, we should see this change in pressure loss. However, there's a lot of cases where we don't have those same correlations or those same models in place. For example, if you have custom equipment, I recently talked with a prospect who had 2 pipes that were just welded together at a 90-degree angle, where that may not have the same correlations that a standard threaded elbow might have. Heat exchangers, especially things like plate heat exchangers or heat exchangers that have fouling and other degradation, that can be better captured with a resistance curve than with a K-factor that you're guessing at. Other components like sensors, filters, again, anything that doesn't fit neatly into any of these categories, you can capture with a resistance curve because all that we need is a point of pressure loss or head loss at a specific flow rate. Another thing to consider is components without a data sheet. Let's say that you're calibrating your system or you're calibrating your model to an existing system, and over time, the quality of data is eroded and you lose track of what specific valve you have in the system. So with that in mind, if you can easily determine the amount of head loss at a given flow rate, we can figure out how do we model that as a resistance curve instead. Finally, as I mentioned, components can degrade over time, especially with heat exchangers and equipment fouling, where the spec sheet may no longer be accurate. So especially in cases of calibration where you're looking at your model, trying to represent that model as accurately as possible, or represent your system as accurately as possible, you want to account for that degradation, and the best way to do that is by capturing it with a resistance curve. So the better agreement we can get between our model and our system, the better our recommendations will be once we start modifying that system, and again, gives us better certainty. A common concept we come back to is garbage in equals garbage out. Resistance curves are just another way that we can reduce the amount of uncertainty going into the input of our model to better trust our output results. So one other thing I want to note is we can also define all of these components with resistance curves as well. So we'll briefly go into the software. And here we're looking in AFT Fathom, but again, all of these resistance curve concepts that we're going to talk about today also apply to AFT Aero and AFT Impulse and AFT Extreme. So here is the range of different components that we can model with a resistance curve in our AFT software. So with valve losses, for example, we could use valve data sheets to specify a CV, or we could use a K-factor instead if we have a kind of rule of thumb K-factor. But again, in the effort of perfectly calibrating a model, especially if you do know a head loss at a flow rate, you can define those components with the resistance curve rather than determining what the equivalent CV is or the equivalent K-factor. It saves you that step. So we can do that with a valve, with a lot of our other valve components like relief valves as well, orifices, screens, sprays. Heat exchangers are a very common one that you would define with a resistance curve. And again, in a lot of cases, as we mentioned, your component may not fit neatly into any of these types of components. So one thing that we would recommend is using this general component, which you can see down here on the lower right of the toolbox. And that is sort of the jack of all trades. This is a component that doesn't neatly fit into anything else, like your filters, like other screens or sensors, things like that, where again, you can define this as a K-factor or as a resistance curve. So again, it's pretty robust. You can use it in a lot of different places and in a lot of different cases. And again, generally, if you have that information at hand, assuming that the information is accurate for pressure loss across a component at a given flow rate, you can use a resistance curve to define that within your model. So what information do we need to define a resistance curve? We've alluded to it a few different times, but we can put it exactly. So in our case, we only need a single point. We only need one measurement of pressure loss at a specific flow rate. We can do that because we already know that second point. We know that we have to have zero pressure loss at zero flow. Again, because if there's no flow through a component, it can't create frictional losses. So with that, let's say in this case, we have a head loss measurement of 10 feet at a flow rate of 100 gallons per minute. We can then say we have this 0, 0 point. We can fit these two to a quadratic curve. And from there, we have our resistance curve to use in our model. So one thing to note is we could add additional points. Let's say that we had a range of flow rate measurements and a range of head losses. We can also fit that quadratic curve through all of those data points as well. One thing to note is by doing this curve fitting, we don't match the data points exactly, or we may not use the data points that are input by the user exactly in the solvent, in the final solution. So if, for example, we had 80 and 10, and then 120 and 12, It's unlikely that if we operate at exactly 80, it's going to provide that 10 feet of head loss, because the curve fit would intersect both of those points and it would rely on whatever that coefficient that we curve fit was. So that's just one caveat to note. Again, it's going to determine what equation we have here, and it's going to use this relationship to define all other points at all other flow rates. So we can define this resistance curve in a few different ways. Most commonly, and what is most recommended, is defining it in terms of head loss and flow rate. Similar to pump curves, you want to look at head because it's a per mass energy. So as we'll see in a moment, if we look at defining a curve in terms of pressure versus in terms of head, we can see how that can impact our results if we start changing the fluid that we're using. However, we do have those options. We can enter it in as pressure loss versus flow rate. We can also use mass flow. And we also have other options to define it in terms of upstream velocity or Reynolds number to characterize that resistance curve. So rather than volumetric flow rate, we could use mass flow, velocity, Reynolds number, and then instead of head, we could also use pressure. However, those two have the caveat that the resistance curve that you would specify is valid only for the fluid that you measured that data for. So let's say that you have a test stand and you're doing all of your testing in water, but in reality, it's going to be installed into an oil system. Head will be able to resolve that discrepancy, whereas the pressure losses will be different because the densities of the fluid will be different. And we'll touch on that here in a moment. But first, let's look at how resistance curves can generate our results and what behavior we would expect to see once we define a resistance curve in our system. So we'll go into our base scenario, where here we have a very simple system. We have just atmospheric pressure, where we're going to 0 psig. We have two relatively arbitrary lengths of piping, just 4 inches and 15 feet. And we're assigning the flow through the system to 100 gallons per minute. So this 100 gallons per minute, this allows us to effectively choose where on that resistance curve that we're operating so that we can manipulate it and see what is going to be our head loss and what's going to be our respective pressure loss through that component. Here our resistance curve is already defined, but we'll go through that definition process again. So we will clear it real quick. And again, we're representing this as a general component because this could be some arbitrary unknown thing where we do know the pressure loss information, but it doesn't fit neatly into any of these pre-existing junctions or pre-existing correlations. So within the general component, under loss model, we can update it to resistance curve. And here we can enter our curve data, where again, all that we need is a single point. So in this case, we know our operating or our measured data was at 100 gallons per minute, and we see 10 feet of head loss. So if we click fill as quadratic, again, it's going to do two things. It's going to assume that 0, 0 point, which makes sense. No flow equals no friction loss. And then that quadratic relationship based on this input point. Over here, if we generate our curve fit, again, if we had more data points, it would curve fit to those various data points, again, fitting that quadratic relationship. And the more data points you have, the more opportunity there is to kind of run into issues. So even if you don't measure 0, 0 as a point, it's a good idea to include that in your specification. But here we have our resistance curve that we're going to use for our model. Again, 100 gallons per minute is what our system is set to flow. So we should see 10 feet of head loss through this component if we did everything correctly. So if we hit OK again, we run our model. If we go and take a look at our output, here I'm going to split the windows so that we can still see our simple system. And we want to look at the pressure losses through J2. So down here, we can look at our junction output. We can go to the general component, and if we zoom in a bit, we can see at 100 gallons per minute, we're seeing that 10 feet of head loss. So again, relatively simple. If we were to change this flow rate, let's say that we double our flow rate, where now instead of 100 gallons per minute, we're running at 200 gallons per minute, we should expect to see, again, not double our pressure loss, but quadruple our pressure loss because of that quadratic relationship. And now when we do our scenario comparison for our 200 gallons per minute, we see that 40 feet of head loss through component 2, which we've defined with our resistance curve. So again, as you change other points in your system, let's say you're changing how your pump is operating, if we were to replace the pipe losses through here, we would want to adjust this pressure loss through this general component. One pitfall that we'll see is it's very common for people to set a fixed head loss at a wide range of flow rates within a resistance curve, but that can run into issues, and we instead recommend defining that with a control valve. But we'll touch on that again a little bit later in the presentation. So the next thing to compare is looking at defining our curve as head loss versus as pressure loss. So here, component 2, we're looking at the exact same curve that we've been looking at, defined in terms of head and then defined in terms of flow rate. And we've generated the second curve based on those results. So here, rather than defining it in terms of head, we're now defining it in terms of pressure loss, where this 4.33 PSID at 100 gallons per minute that I got from our previous results. So if we go back, we run our model, we can look at our output. If we wanted to look at the pressure loss through our components, let's see. So the DP would be, again, here's that 4.3. And here, if we run our model comparing our head loss versus flow rate, again, at 100 gallons per minute, so we reset the system, both of these are going to be operating at 100 gallons per minute. Because of how we've set it up, we should see the exact same results through each of these components. So when we run our model and we go to our output, and again, we can compare those two general components. So when we've defined it in terms of head loss, we still see that same 10 feet of head loss in our results. When we defined it in terms of pressure, here we would really look at 100 gallons per minute and that 4.33 PSID that we've defined within our resistance curve. So as long as the fluid is the same for each of these curves, we would expect the results to be the same, again, assuming that the pressure loss data that we used or that we collected to generate this resistance curve was generated from the fluid that we're modeling within the system. So obviously, if you're using water, that's a very common fluid. It's probably okay to define it in terms of pressure loss, assuming that your system is also going to be flowing water. But something that we can look at is if we instead change our fluid, where now the amount of head loss per amount of pressure loss is going to vary, and it's going to vary based on the density of the fluid. So here again, we have that same system, but we're going to change the fluid, and in this case, we're going to be pumping methane instead. So we haven't changed anything in the system besides our fluid. Our resistance curves are still 10 feet of head loss at 100 gallons per minute, and our pressure loss curve is still that 4.33 PSI at 100 gallons per minute. However, for lower density fluids, they're going to have a smaller pressure drop at the same head loss compared to a more dense fluid, and they're going to see a larger head loss for the same pressure drop. So here, if we look at this relationship, this is, if you remember Bernoulli's equation, this is one of the components of it, where you can move between pressure and head in this way by adding gravity. And then here, we don't use rho, but this P is representing that density component. So if we run our model, again, in the case of water, where the pressure curve was defined in terms of water and the fluid was still water, we got the same results. But now if we compare our general components, we can see that we're still getting our 10 feet of head loss through the first one, and we're still getting our 4.33 PSI of pressure loss through the second one. But now we see this inconsistency in head, and we also see this inconsistency in pressure. So again, it's important to consider the density of the fluid, and this is where the idea of reference density comes in. How can we modify the curve that we've input so that way it's applicable to any fluids, in essence, converting from pressure into head, so that way we can take that information, plug it into whatever system, whatever fluid that we're modeling. So again, reference density, in general, the idea would be defining all of your resistance curves in terms of head and flow rate, because otherwise, by defining it in terms of mass flow or pressure, you're now assuming something about the density of the fluid. It's no longer a per mass energy transfer. It's now, here's the results, here's the density, here's the actual mass that's going through our fluid. So what we can do is add this reference density component, and that way we can adjust it. So if all of our testing was with water, if we have that pressure loss data, this tool or this reference density will effectively convert it into a head flow rate, and then also into a head loss, and then also into a volumetric flow rate. So the reference density is the density used while testing and creating the curve, again, moving from whatever the actual pressure loss that you measured was to a head loss, or the mass flow to that volumetric flow. Note that this is only necessary if your system and test fluids are different. Again, if the density is the same, then the mass energy transfer is going to be the same. And so it's really only necessary, as we saw when we changed from water to methane, and that's where we started to see that discrepancy in results. If we think of pumps, again, hopefully you've defined a pump curve at some point, but there's a reason that those are defined in terms of head rather than pressure rise. And that's so that the energy added, or the operation of the pump, is independent of the fluid's density, of whatever they were testing it with, and then again, of whatever you are pumping through that pump. That's why you can see drastically different pressure rises for the same pump at the same speed, but you should see the same head rise across both of them. So same thing here with this resistance curve, and with this reference density, is trying to take it from that more specific, given the density, how do you make that independent so it works with any fluid? So to do this in the software, again, anytime that you define a resistance curve in terms of pressure or in terms of mass flow, what you'll see is this reference density box appear and be allowed for input. So here we have no correction. Again, this is fine if the fluid that we're pumping through this component is the same fluid as through our system. However, again, once you change it, there's where the problem occurs, but you can specify the reference density yourself, or a very common one, if you are testing with water, we provide that density for you automatically. So if we think back, because we generated this DP curve based on our losses with water, again, we could have taken that 10 feet of head loss, and then the calculated DP, and then we put that in to our P versus Q. We can say that our reference density, because we tested with water, is water at STP. So here in this scenario, what we've done is this reference density, we've checked water. So now, instead of using pressure, we can use the density of water, convert that to a head, and then use that for all of our subsequent calculations. So now when we run our model, if we look at our results for our general component, we see one, our DH is now effectively the same. This DH probably has a slight variation if our original conditions weren't exactly at STP. And then we can also see that now our DP across the component is the same. So even though we specified here our 4.33 PSID at 100 gallons per minute, it's no longer using this exact DP curve, because it's now converted it to head, and we can back calculate what that DP will be at that point. So reference density, again, really only important if the data that you have for a component is for a fluid different from the system that you put that component into. And we can see how those results changed. Again, the pressure loss can be the same, but depending on the density, you may see a much higher head loss or a much lower head loss, depending on the relative density of your test fluid and of your fluid in your actual system. One thing I want to note is we also have documentation on everything that we're going to talk about today. So within our help site, which you can go to from docs.aft.com, here we can go to the Fathom help site, and if we look up reference pressure, or reference density, I should say, and we search, here we can see that we have that same page that'll go through those same concepts. So this is useful if you need a refresher, or if you're having a tough understanding the difference between that pressure drop and the head loss relationship. But We'll come back to the documentation when we talk a little bit more about pitfalls and then troubleshooting resistance curves as well. So by now, hopefully we're familiar with the shape of the resistance curve. Anything that does not follow that quadratic shape should be a red flag in your mind. So here are some examples of resistance curves that I would consider misinput, where this point we can see it has that 0, 0 loss. It has technically a quadratic curve, but we should see an increase in friction as flow rate increases, not a sudden decrease. We can also see here a flat line, where, as I mentioned, this fixed head loss or this fixed pressure loss component would be better modeled as a constant pressure drop control valve, where you can say, regardless of the flow rate coming into or out of that component, we're going to see 2 feet of head across it. In a lot of cases, having a very flat head loss like this can lead to convergence issues, as we'll see in the troubleshooting section in just a moment. The second point is when curves miss the 0 pressure loss at 0 flow rate point. Talking with a NASA engineer during a training class, they mentioned that creating pressure loss at 0 flow, effectively you're just creating energy. So if you can do this, if your measurements can prove this, you should patent that component because you've created infinite energy. But in the same way, here we can see this resistance curve has that quadratic shape that we're looking for. However, it misses that 0, 0, so we're creating a head loss, even though there's no flow to create the friction to cause that head loss. So those are common pitfalls. This too has a documentation page about things that you should be aware of with those resistance curves with these same figures as well. The final piece is troubleshooting. So adding resistance curves, they're a relatively simple definition, but they can introduce convergence issues into your model, especially if you are running into convergence issues where your model iterates and iterates and it doesn't seem to approach a solution. You may want to double check your resistance curves in addition to other things like detail T's and other specifications. So during troubleshooting, the first thing you should do is verify the shape of the resistance curve. Again, looking for that increasing quadratic shape and that 0, 0.0 frictional pressure loss if there's 0 flow. The next thing is to verify the units of your resistance curves. So while it may be a relatively minor misinput, let's say you did atmospheres instead of bars, or more dramatically PSIG instead of bar, that can lead to a very large discrepancy just because of the kind of dramatic difference in the units themselves. So that's another thing to consider. Third, check the reference density if your system fluid is different from your test fluid. Not to belabor the point any further, again, we can see that discrepancy where at the same head loss, we should expect different pressure losses for different fluids. So defining a curve in terms of pressure or in terms of mass flow rate, that can lead to uncertainty if the test data is different from the fluid data. So these effects are generally going to be harder to identify and harder to troubleshoot. But again, knowing that you've defined resistance curves into your model, this is an area that I would go and check, especially if you're running into convergence issues or results that are unclear or unexpected. Finally, resistance curves may be used for components that are run in parallel. So for example, if you have a series of heat exchangers or a wide cooling water system where it goes out and branches to a lot of different heat exchangers, you want to make sure that those components have similarity between them, especially if the components are very close to each other and they're all in parallel. That can lead to a kind of challenging flow solution for the system to converge on. So double checking that all of those components, if they are the same component in the physical system, they should be represented with the same resistance curve in your model. So just a few troubleshooting tips. Again, by understanding kind of the need and what a resistance curve is representing during input, you can avoid a lot of these issues. Again, making sure it follows that quadratic shape, using head loss and flow rate generally better than using pressure or mass flow rate. Again, we can correct that using reference density, and then we want to make sure that if we have common components, they're all going to see the same losses across each of them. So again, as I mentioned, it's a relatively brief webinar. Hopefully you have some opportunities to implement resistance curves into your own systems, but let's review. Resistance curves are valuable when you, for example, need to represent a component that doesn't neatly fit into another loss model. Common cases are heat exchangers or cases where you may not have datasheet information. If you have field data to represent a component, generally the closer you can get to actual field measured data, the more representative your model will be. And then also if you have concerns about component degradation, if you have a valve but the valve is 50 years old or your pipes are scaled in your heat exchanger, it may be more reliable to represent it with a resistance curve, having a known pressure or head loss and a known flow rate rather than using an assumed K factor or an outdated data sheet. You only need a single point, so you only need to know 1 point of head loss and flow rate to define a resistance curve. And then again, you want to be aware of the impact of density if you are defining in terms of pressure or mass flow rate, using that reference density to correct for it and get it to a head loss and flow rate relationship instead. We saw that you can define many junctions with resistance curves instead. So if you don't know orifice areas or valve CVs, again, if you have the ability to take a measurement and you trust that that measurement is accurate, that should be more representative in your model of what the system is going to do and how that component is going to respond once you start changing other variables in your system. And then again, if you take nothing else from this webinar, all these resistance curves should have that same shape. You want to look out for that 0, 0 point, and you want to see that increasing quadratic curve. Any other shape is probably wrong or maybe better represented with a different component, as we saw with the constant pressure drop control valve. So I want to thank everyone for attending. If you have any other questions, feel free to send us an email at webinars@aft.com and we'll do our best to get you a response. If you have any ideas for future webinars or future topics, whether that be an industry that you're working in, a particular problem that you're having, or a common point that you teach your own engineers during training, feel free to shoot it over and we're happy to put together a webinar, again, try to bring more knowledge to our wider user base. If you've made it to the end of the webinar, I want to thank you for your time. And of course, if you have any other questions, feel free to give us a shout and we look forward to having you in a future AFT webinar sometime soon. Thanks again.